Have you ever been on a curvy road and wondered, what's actually keeping the car from flying off into the scenery? Today, we're going to get into the physics of a winding road and figure out exactly how fast is too fast.
I think we've all been there, right? You go into a corner, maybe a little too quick, and you can feel the tires just start to complain. But what is the physics that decides that exact moment when your tires lose their grip and the car starts to slide? Well, that's precisely what we're going to pin down today.
So here it is, the problem straight from Irodov's classic physics textbook. Now, I know it looks a little intimidating with all those variables like A and alpha, but don't worry. All those are doing is just describing the shape of our road, how sharp the curves are and how long and stretched out they are. The real question is pretty simple. What's the ultimate speed limit here to avoid sliding? Let's break this thing down. Okay, here's our game plan. We're going to tackle this in 6 pieces. We'll start with the forces at play, then we'll get into the weirdness of acceleration on a curve, and finally, we'll put it all together to calculate that speed limit. By the time you're done, you won't just have the answer, you'll actually get what it means for driving in the real world. All right, first things first. Just like any physics problem with things moving around, our first job is to figure out all the forces acting on the car. And for that, a free body diagram is our best friend. So, on a nice flat road, you've got gravity pulling the car down and the normal force from the road pushing right back up. Simple enough, they cancel each other out. But the really interesting force, the hero of our story today, is friction. It's the only force pushing sideways on the car, and it's the only thing that's going to make it follow that curve instead of just going straight. And here is a super common place to get tripped up, so let's clear it up right now. We are dealing with static friction. I know what you're thinking. Wait, but the car is moving. And you're right, it is. But the little patch of tire that's actually touching the road at any given instant is momentarily stationary. It's gripping, not slipping. The second your car starts to skid, that's when kinetic friction comes into play. And frankly, by then, you're already in trouble. Okay, let's move on to our next big idea, acceleration. The problem says the car is moving uniformly. Now, that's kind of a trick word in physics. It means the car's speed is constant, but as you're about to see, that absolutely does not mean there's no acceleration. Yep, if you were to look down at the speedometer, that needle is holding perfectly still. The magnitude, the number value of your velocity, isn't changing. But here's the catch. Velocity isn't just a number. It's what we call a vector. It has both a magnitude, that's your speed, and a direction. And because our car is on a winding road, its direction is constantly, continuously changing. Any change in velocity, even if it's only a change in direction, means the car is accelerating. We have a special name for this kind of acceleration. It's called centripetal acceleration, and it's always pointing toward the center of the curve. And of course, thanks to good old Newton's second law, F equals ma, we know that if there's an acceleration, there has to be a force causing it. And what's that force in our case? You guessed it, it's that static friction we were just talking about. So let's dig into the shape of this curve itself. The amount of force you need to make a turn depends on how sharp that turn is. We measure that sharpness with something called the radius of curvature, which we'll call r. Now, for a perfect circle, r is just the radius, easy. But on our wavy sine curve road, the curve is tighter in some spots and gentler in others, so that r value is always changing. Now, think about it. If we want to find the absolute maximum speed the car can handle on this entire road, we can't just pick a random spot. We have to look at the worst-case scenario. And that means we've got to find the tightest, sharpest part of the curve, the spot where the radius of curvature is the smallest, because that's the point that demands the most force from the tires to keep the car on the road. So how in the world do we find that sharpest point? Well, this is where a little bit of calculus comes into play. Now, don't let that formula on the screen scare you. The process is actually pretty logical. We just take the equation for our road, find its first and second derivatives, and then we plug them into this standard formula. This tells us the radius of the curve at any point we want. And it turns out the minimum radius, the sharpest turn, happens right at the very peak of each wave. And after we run through all that math, we get this surprisingly simple little result. The minimum radius of curvature, the sharpest bit of our whole road, is just that constant alpha squared divided by the constant a. Pretty neat. Okay, we are on the home stretch now. We've got our forces, we understand the whole acceleration thing, and we've even found the sharpest part of the curve. So it's time to put all these pieces together and actually calculate that speed limit.
The whole problem really boils down to this. It's a balancing act. On one side of the scale, you have the maximum turning force your tires can possibly provide. That's the static friction, which is the coefficient, Ks, times the normal force, mg. And on the other side of the scale, you have the force you need to make that sharpest turn. That's the centripetal force, which is the mass times v squared over our minimum radius, r men. So, to stay on the road, the force you have available has to be at least as big as the force you require. This right here is our critical condition. And notice something really cool here. The mass, m, is on both sides of the equation. So it just cancels out. That means the safe speed limit is actually the same for a tiny little sports car as it is for a giant truck, as long as they have the same tires. All right, this is it. The final step. All we have to do is take our expression for that minimum radius, r min, plug it into our inequality, and then solve for v. That will give us the top speed for this entire road. And there you have it. That's our final answer. The maximum safe velocity is alpha times the square root of k times g, all divided by a. This elegant little formula tells us exactly how fast we can go without sliding off this winding road. But you know, just staring at a bunch of symbols isn't the real point. What does this equation actually tell us? Let's translate this math back into the real world. What does each one of those letters mean for someone behind the wheel? This is where it all clicks. Our formula actually confirms what our gut tells us about driving. If you have a higher K, stick your tires or grip your road, you can go faster. Makes sense. If you have a larger alpha, that means the curves are longer and more gentle, so you can go faster. Also makes sense. But if you have a larger A, that means the peaks are sharper, more aggressive, and you have to slow down. The formula just perfectly captures all of that. And just for fun, look at G in there, gravity. On a planet with stronger gravity, you could actually take turns faster because the extra weight would give you more grip. So the next time you're driving on a winding road, you'll see it a little differently. It's not just a road, it's a physics problem in motion. It's really just a beautiful example of how a few fundamental ideas, like F equals m and friction, control the world around us. So what do you think? How would you design a faster racetrack? Thanks for joining me for this explainer.